we're going to use the spectral representation to give us a means of calculating a function of a square matrix. An alternate way of doing this spectral computing functions of a square matrix is using what's called spectral mapping. So this is an alternate way of doing that. We first start with the characteristic polynomial of our matrix A, determinant of Si minus A. In general, this is going to be an nth order polynomial, and in general, when we factor it, we might get repeated roots. So here lambdas are the eigenvalues, and they may be repeated. Each one may be repeated by some number. So in general, we may have m distinct values, and they are repeated a certain number of times. So given this representation, we can write down that A can be written this way. Again, there are m terms, distinct terms. Lambda k, so there are m distinct lambdas, multiplying by some projection matrix plus a nilpotent matrix. The projection ek, the kth projection matrix is called an eigenspace projection, and the n matrix, the nilpotent matrix, is called an eigenspace nilpotent matrix. The matrix E can be formed by eigenvectors. You can form the matrix E by computing right and left eigenvectors associated with the eigenvalue lambda. So if you compute the right and left eigenvectors, you can form E from them. So I'm not going to talk much about it. I'm going to show a different way of computing it, but that's one way of computing it. So you have these projections, you have these nilpotent matrices. What about these projections and these nilpotent matrices? Well, they actually have quite a few important properties. In terms of the eigenspace projection matrices, all of them are projections, so that's each one, if you square it, you get the matrix back. The sum of the projection matrices add up to the identity matrix. Okay, so that's an important property. The E's add up to the identity matrix. So one way of writing the identity matrix is actually a sum of the E's. Ej is equal to delta ij ei. So what is that? What this is basically saying is, so notice if I is equal to j, then we actually have e squared, and that's basically the same property here. It's equal to itself, right? So delta is 1 if I is equal to j. Delta ij is 0 if I is not equal to j. So if I is equal to j, we get the matrix back. If I is not equal to j, then we'll get 0. That's what this is saying. And finally, we see that each of the projection matrices commutes with the A matrix. Okay. In fact, we can go through and show that each of the projection matrices can be written as a polynomial in the matrix A. As for the eigenspace nilpotent matrices, if we raise each, so if you recall characteristic polynomial, each of the lambdas is repeated nk times. If you raise the nilpotent matrix to the power nk, you will get 0. So this is actually, this is the nilpotent property. But in general, nk is going to be less than n, okay, because you have multiple of these guys, and so in general you will have that. Then you have this relationship, Niej is equal to Ejni, which is equal to delta ij ni. So what is this saying? Well, if I is equal to j, then we get ni back. So ej times ni is equal to ni. So in that case, these matrices commute. And if I is not equal to j, then it's equal to 0. So if an n is multiplied by an e where they're not from the same eigenvalue, then you will get 0. Otherwise, you will get the nilpotent matrix back. Also, if you multiply the nilpotent matrices by each other, you will get 0 whenever they're not from the same eigenvalue. And you can also show that the nilpotent matrix can be written in terms of E in this way. Okay, so we can, if we've found the E's, then we can find the N's this way. So how do we find the E's? Well, it's not with complete ease. We take the characteristic polynomial, 1 over the characteristic polynomial. If we then, again, the characteristic polynomial can be factored, we can take this and do a partial fraction expansion kind of thing this way, where if we do a full partial fraction expansion, so let's suppose s minus lambda 1 is raised to the 3rd power, then we will get 3 terms in that partial fraction expansion. Something over s minus lambda 1, something over s minus lambda 1 squared, quantity squared, something over s plus s minus lambda 1 quantity cubed. You'll get the 3 terms. If you put those together, those 3 terms together, find the common denominator, which is going to be s minus lambda 1 to the cube, and then you have to set the denominator so that they're all equal, and then add them up. In general, you'll get a polynomial here in the numerator. And if you do that with each of the m eigenvalues, you will get m polynomials, x1 through xm, and the degree of each of these x's is less than the degree of the n. Okay, so this is a property of the x's. So x's are polynomials in S. We can also define the polynomials pi as p of s with the ith term missing. So remember, p of s is the product of these guys, and if we remove one of these guys, if you remove one of the factors, that is p of s, pi of s. So if you look at this summation and put it all over a common denominator, the common denominator is p of s, then you will get this expression, x1 times p1 all the way down to xm times pm. And this denominator clearly is p of s. This numerator, however, surprisingly is equal to 1. Okay, so the sum of all this stuff in the numerator must be equal to 1, because when we did the partial fraction expansion, this was equal to this, right? So when you put it all over a common denominator, which is p of s, we get this stuff, all of which must be equal to 1. So we have this polynomial equation. It sounds like a lot of work at this point. So what is this bias? Well, if we set ei, if we create a polynomial little ei of s to be xi of s, pi of s, then we can go through and show, so this is x1 of s, this is xm of s, the sum is equal to 1. Okay, and now we can set ei equal little ei evaluated at a, and so instead of being a function of s, it's a function of a, and then we can define the nilpotent matrices this way once we've got the ei's, and a then can be written this way. Okay, so when we do that partial fraction expansion, that gives us the polynomials that we need, and those polynomials then give us the projection matrices that we need. So here I've written A out this form. We can expand it to see this way. You have lambda 1 E1 plus N1 all the way down to lambda m EM plus NM. Incidentally, some of these n's might be 0, in which case this whole expression can simplify. So this is the spectral representation. Okay, so we found the spectral representation. Now, how does that help us compute a function of a polynomial? Well, here in general, we have a function of x. So if we have an analytic function in x, we can get its Taylor expansion. Okay, so this is the Taylor expansion of a function around some value lambda. Now I haven't specified what lambda is, but clearly lambda is going to be related to the eigenvalues. We'll come back later too. So this is the Taylor expansion, and in general it sums up to infinity. And you take the derivative of the function, the kth derivative of the function evaluated at lambda, multiplied by x minus lambda to the power k. Okay? So now if we take f of lambda, that's equal to, f of a is equal to I times f of a. But I remember the identity can be written as the sum of the E matrices. Okay? So now I have this sum multiplied by this sum. So this is an infinite summation. This is a finite summation, but I'm going to multiply an infinite summation by a finite summation. I'll still get an infinite summation. Okay? So again, I times f is going to give the projection matrices times f of a. So I can distribute them through this way. I can distribute them through. So I is the sum of the projection matrices. So I distribute them through and I get this expression. EI times the function at A. What does that look like? So each of these terms is of this form. Okay, so if I take f of A, which is the power series that we had, and I now multiply through by a matrix on the left. So notice that I can bring that EI inside the summation. This is just a scalar, this is just a scalar, and so I can move it past those over to this side. And so we can see then that this quantity here is EI A minus lambda I times the identity matrix. That quantity is the nilpotent matrix Ni. So Ni raised to the power k. And so we get this. So this is an infinite summation. But remember, because this is a nilpotent matrix, when we raise a nilpotent matrix past a certain power, it becomes 0. In fact, for Ni, if we raise it past the power little ni, we will get 0. And so this infinite summation becomes a finite summation up to ni, little ni minus 1. From 0 up to little ni minus 1. So this infinite Taylor expansion simplifies down to a finite expansion. Okay, so basically we're evaluating this at little lambda I when we do this. So this is the expression that's true for each one of these guys. And so overall, the function, which is the sum of all of these guys, I now have, again, I'm taking the sum of each of these guys from n1 to nm, and I can combine this as a double sum, and this is what I get. So these are finite summations, not an infinite summation. And so we've simplified the whole expression down. And so this is what it looks like if we expand it out. So notice that when we take the derivative, we're actually taking the derivative with respect to x of the function f of x and then evaluating it at the eigenvalue. Okay, and so this is the spectral representation, which looks kind of like a mess. We'll go through and work some examples, and we'll find that it's actually not that bad. And actually, it's helpful to have the EIs and the NIs to work with. So this is the spectral representation.